All right, and let's do a screen share here. Okay, what I think I'm going to do is go back to my notes. I'm going to pick up with the notes that we finished last time. All right. By the way, I think lab went fine. Everybody seemed to be well in the groove last night, I would say. So things were moving along pretty good. I'll be curious to see once you start generating some of these pH plots, how they look. So that'll be interesting to see. And if anybody has any questions about that before the lab is due next week, feel free to come by around on the office hours, share your screen with me and sort of let me see what's going on if need be, because I'm kind of curious to see how your data look as well. All right, so everybody hear me okay? I always get worried when I hear silence on the other end.
Yep, it's good.
Yeah.
All right, beautiful. All right, so I just kind of want to review this example that we started last time, because we want to sort of finish it today and then move on from there, do some more buffer related stuff that we can do. And this next example I'm going to do after this actually ties into your next homework assignment, which I'm still sort of engineering for you. It won't be due for another couple of weeks, so don't freak out. But basically, it's going to be essentially a homework version of the buffer lab that we normally do. So what's going to happen there is that everybody's going to get a different buffer to make. And you're going to have to tell me how you're going to make that buffer to satisfy a specific pH. So the third example will be an excellent template for doing that. So we're going to kind of go over that. And when I hand you the homework, make sure you're referring back to example number 3. But anyway, example number 2 is what we want to deal with. So just to review it very quickly. So we want to know what the pH of a buffer is in example 1. So we actually set that buffer up to begin with. If 50 mils of 1 molar nitric acid were added to it. Okay, so what we had was a buffer consisting of, what was it, ammonia and ammonium. That's down there in the next table. Okay, so you can go back to example 1 to determine that. All right, and keep in mind what we're doing here is we're adding some volume of a strong acid to that buffer. So we know what's going to happen. The acid is going to react with the base part of the buffer and chew some of it up and make some of the acid part of the buffer. That's what happens. All right, so I'm taking 50 mils of 1 molar nitric acid, and you can see the dissociation equation for the nitric acid here. Okay, so it dissociates 100% in acid because it's a strong acid, right? And it's going to give me hydronium ion. Now, I give you a molarity and a volume. So you guys know that if you have a molarity and a volume, you can get moles or millimoles or whatever you want to work with here. So I did it in terms of millimoles and converted it to moles. So basically what we've got here is the moles of hydronium ion that actually got added to the buffer. Now, the reason I did this is because in many buffer calculations, if it's convenient to do so, we can work in terms of moles. Okay, we don't have to work in terms of molarities if, for example, we're after a pH, okay? And Henderson-Hasselbalch allows us to do that, and we'll show that here in just a little bit why that's true. But essentially what's happening here is we want to set up the reaction that's happening between the base part of the buffer, which is the ammonia, and the strong acid we're adding, which is the hydronium that comes from the dissociation of the nitric acid. Now, of course, you can write that as just a standard Bronsted-Lowry acid-base reaction where the strong acid is going to donate a proton to the base. So you're going to make water and you're going to make ammonium ion, okay? Now, we said this reaction goes 100% to the right. Why is that? Well, it's because we have a weak base reacting with a strong acid. So remember, weak plus strong goes 100% to the right. Why is that? It's because that reaction has a very large K. In fact, it's 1 over the Ka for the ammonium ion. The K for the ammonium ion is a very small value. So if you take the inverse of it, you're going to get a really big number. All right. So basically what we have is a limiting reactant problem. So this is the first time you've seen this kind of table. This is just another way of essentially looking at a limiting reactant problem. And we can set it up as what we call an ICF table. It's like an ICE table. So we're used to doing ICE tables now, and ICF tables work exactly the same way. It's just that F now is the final non-equilibrium based concentration of everything in solution. All right, so it's like the E line in an ICE table. So what do? I can do this either in terms of molarities like we normally do in an ICE table, but I can do ICF tables in terms of moles as well if I want to. Okay, doesn't matter. Now, why do I do ICE tables in terms of concentrations? Well, that's because ultimately the E line of the ICE table goes into the law of mass action. And what are the units of things in the law of mass action? Well, it's molar concentrations, right? So that's why we do that. But here, since we're not plugging anything into the law of mass action, we can use moles. All right, so just looking at the table again. All right, so if you go back to example number 1, I had 1 liter of the buffer and it was 0.150 molar in ammonia. All right, so if I have 1 liter, that means I've got 0.150 moles of the ammonia. We could do the same thing with the ammonium. It was 0.258 molar in ammonium ion, but I had 1 liter of it. So I can assume I've got 0.258 moles of ammonium ion. And I had the moles of the hydronium ion there from the dissociation reaction of the nitric acid, which we just calculated. So you look at that and you can say, okay, everything's 1-to-1 stoichiometry throughout. So ultimately, we know who the limiting reactant is. It's the thing we have fewer moles of, right? So in this case, that's got to be the hydronium ion. So if we let the reaction go 100% to the right, we're going to use up all of the limiting reactants. We have no hydronium left. We're going to use up that amount of the ammonia, right? Because it's a 1-to-1 stoichiometric relationship. So you're going to end up in the F line with having 1/10 of a mole left of the ammonia. And then, of course, you're adding on the right-hand side, right? Because that's a product that you're making. So you're starting out with 0.258 moles of the ammonium ion, but you're adding 0.05 to that because that's the product of the reaction stoichiometrically as you convert the ammonia to ammonium through the hydronium ion. Add those up, you get 0.308. So now what those correspond to are final concentrations in the mixture, okay? So now you can see essentially what you've done to the buffer. Look at the difference between the I line and the F line for the ammonia and the ammonium. Notice what happened. The ammonia concentration or number of moles has gone down, but the ammonium concentration or number of moles has gone up. But have they gone up appreciably or gone down appreciably? Not really, okay? So do I still have a buffer here? In other words, even after I've added the acid, do I still have a mixture of a weak base and its conjugate acid? What do you guys think?
Yeah.
Yeah, sure do. It's still there. I still got ammonia. I still got ammonium. So now I want to go out about finding the new pH. So how would I do it? There's several ways I could do it, but what's one way you might suggest that I do this?
Use Henderson-Hasselbalch.
Yeah, I could use Henderson-Hasselbalch, sure. So let's just go ahead and write that out. And that works anytime I have a buffer. So pH is equal to pKa plus the log, right? Base 10 log of the base part over the acid part. Oh, well, what's the base part here? It's the ammonia. And here's what I'm going to do. I'm going to do it in terms of the moles of the base divided by the moles of the acid part of the buffer. Okay, so why am I able to use moles in Henderson-Hasselbalch? Because when we actually derived Henderson-Hasselbalch, we always said those things were in terms of molar concentrations. So why is it okay for me to use moles here?
It's all going to cancel anyway, and the log doesn't really have an identity.
Yeah, exactly. So basically what's going to happen is the volume's the same, right? So you could say that molarity is going to be proportional to number of moles of each thing. Okay, and the volume is the same. So essentially what's going to happen is the volume part of molarity cancels out. So that's why I can use moles in Henderson-Hasselbalch. So keep that in mind. As far as and that's exactly right. We're taking a ratio, and with moles being proportional to molarity, okay, they're going to ratio out the same way, okay? So that's what's going to work for us. So sometimes it's more convenient to put moles in there, and sometimes it's more convenient to put molarities in there. Depends on what the problem gives us. But keep in mind, you've got some latitude there, guys. So it's easy now. Which pKa am I after? I want the pKa of what? Whose pKa am I looking up?
It would be ammonium.
Which one, ammonia or ammonium?
I said ammonium.
Ammonium, that's what I did. Yeah, you're a little muffled. Yeah, it's always the acid part, right? And the acid part of the buffer is the ammonium. So we need to look up the pK of ammonium. And I did that, okay? So in your textbook, over in the appendix, the ammonium turns out to be 9.244 for the pKa. You can also get it by looking up the negative log of the Ka. That would give it to you as well. Okay, so now it's simple. We're just going to plug everything back into Henderson-Hasselbalch. Okay. All right, so how many moles of NH3 do I have? 0.1. I'm not even going to attach units to this. How many moles of ammonium do I have? 0.308. And again, that's coming from the F line after I've actually done my adjustments. And what you end up getting here for pH, once I work it out, is 8.76. So now the question becomes, did the buffer do its job? How much did the pH change, or did it change? And if it did change, did it change by a lot? All right, so what are we going to do? We're going to go back and compare this to the original buffer that we set up before we added any acid to it. And that was over in what, example number 1? So let's go back and look at example number 1 and see what we got. Was that it? Yeah.
Quick question about your answer for pH. We had three significant figures in the pKa, and then our log we had 0.100 and 0.308, so 3 significant figures there.
Yeah, we should actually end up with another one. Do you agree with me?
Yeah.
Because it looks like I'm going to keep 3. Once I take the ratio of the log 0.1 divided by 0.3, what does that give you?
Negative 0.488, so
okay.
89.
So you're not losing any there. So you're still going to have 3 there. And then when you take the log, so when you take the log, you're still going to have 3 there.
Yeah,
and then
3.
So you should have 1 more on the end. What'd you get?
8.755. So just 2 5s instead of a 6.
Yeah, let's do that. Yep, that would be correct. All right. So what did I say my original pH was? So we just looked at it. 9.009. Was that what it was?
Yeah.
Okay. So what happened to the pH? Did it go up or go down?
Down, but not a crazy amount.
Yeah, exactly. So yeah, it did go down a little bit. You kind of expect it's got to go down a little bit if you're going to add some amount of a strong acid to a solution. But did it go down a crazy amount? No, not at all. Not at all. The difference between, let's say, 8.8 and 9.0 is quite small. Okay, so it looks like the buffer actually did its job, didn't it? It kept us relatively constant in pH, even though we dumped pretty much a boatload of hydronium ion into the mixture. So the buffer's working. All right. Now, we also know that would be true because remember, if you go back up to the F line, which is where we're setting the new concentrations, we're within the capacity of the buffer, aren't we? We've still got some of the weak base and we've still got some of the weak acid there. The ratios of the two have changed a little bit, but not appreciably, right? I've still got some of each, which tells me I've still got a buffer. So I'm within the capacity of the buffer here. Okay. Now, what would happen if I'd added enough hydronium that I ended up with, let's say, 0.18 moles of it? What would happen then?
There would be an X.
Broken.
Well, you'd end up with a different limiting reactant now, wouldn't you? Now the hydronium ion would go into excess and the ammonia would get used up, wouldn't it? So what would I have in solution? I'd have an excess of hydronium, and I'd also have some NH4 plus in there, right? So what's driving the pH in that case?
The hydronium ion.
It's the hydronium ion. It's the excess of the hydronium ion that's driving the pH. So is the buffer working at that point if there's no ammonia left in it?
No.
No, we've broken the buffer down because we've exceeded its capacity, right? So in that case, we no longer have a buffer. We just have an excess of the hydronium ion in solution. You calculate that excess, and then you can calculate a pH directly from that. And that would be a very low number, wouldn't it? So the buffer would be broken down at that point. All right, so that's kind of a good visualization of what I mean by buffer capacity. All right, everybody okay with that? And everybody all right with the idea that we can use moles in Henderson-Hasselbalch instead of molarities when we want to? And I could have worked this problem totally from the perspective of molarity if I'd wanted to, right? I could have gotten my moles of each thing and then accounted for dilution by accounting for the total volume of the solution and calculated all my new molarities. And then I could have plugged those molarities into Henderson-Hasselbalch. Guess what? I'm going to get the same answer, okay? But there's a lot more work involved with that because you have to account for dilution effects. All right, so let's look at another example. And this is the one that's going to really tie into your homework as I sort of see it going. So this will be example number 3. All right, so here's what we got. We're going to say we have a researcher prepares. We'll say must prepare because that's how I've written. 0.50 liters of 3.0 molar nitrite buffer. At pH 3. All right. How are they going to do this? So in other words, what steps does the researcher have to go through to do that? All right. So what do I know? I know my V total for the buffer, right? That's going to be 0.50 liters. What else do I know? I know my target pH. I know where I want the buffer to end up. That's going to be 3.00. And then the other thing I'm given is a concentration, okay? Now that is a 3.0 molar concentration. Now the assumption when we do this is the following. When I say we're going to make a 3.0 molar nitrite buffer, what I really mean here is the 3.0 molar is going to actually be the combined concentration of both species, okay? So it's going to be, we'll say X molar of NO2 1 minus. And that's the base part, right? But a buffer needs an acid part. So what's the conjugate acid of NO2 1 minus?
HNO2?
Yeah, it's nitrous acid. So we'll say Y molar of HNO2, which is the conjugate acid. Right? And that satisfies the definition of a buffer because a buffer has to be a mixture of a weak base and its conjugate acid or a weak acid and its conjugate base. And we've got a conjugate acid base pair here. But the point is the 3.0 molar is going to be the sum total of the concentration of both of those species. Okay? So this is more or less what we're given in the problem. So now we have to do a few things to verify. Okay, so the first thing we want to do is to verify the buffer components. In other words, are these appropriate conjugate acid base pair to choose for this buffer? And we mentioned something about this very briefly in class last time. Okay, so again, let's just sort of look at what we got. Okay, we know that we have the weak base. That's going to be the nitrite. I know I've got my weak acid. That's the nitrous acid, which is HNO2. Okay. Now, what can I look up with regard to the nitrous acid that might be helpful to us? Think about Henderson-Hasselbalch. What other piece of information besides concentrations and such do I have to have in there?
pKa.
pKa, right? And the pKa refers to the acid part. So I need a pKa for this, don't I? So you can go look that up. So the pKa for the acid part of the buffer is 3.39. Okay. So here's the deal. Is this a good choice? Is this a good choice? We need a rule for that, okay? So we might pose the question, is this a good acid conjugate base pair? Is it appropriate for the pH we want to get? Well, here's the rule for determining that. Now, you guys might remember from class last time, I said that to make a really good buffer, you generally want your pKa of your acid to be close to the target pH that you're trying to get, okay? So the rule comes down to that. The rule is this, is that the pH that's your target is equal to your pKa plus or minus 1 pH unit. In other words, your pH equals your pKa plus or minus 1. Okay, so let's see if this actually works. So what did I say my target pH was? It was 3.00, wasn't it? So that's equal to my pKa, which is what, 3.39? And that has to be plus or minus 1, right? So is my 3.39 within plus or minus 1 of 3?
Yep.
Yeah, it's good. It's good. All right. So that means I've got a good conjugate acid base pair. Okay. So here's the deal. When I give you guys your homework problem that's going to be like this, I'm going to give you like 3 or 4 different possible conjugate acid base pairs that you could use. And you're going to have a target pH, and everybody's target pH is going to be different. So out of those 3 or 4 conjugate acid base pairs, the first thing you have to do is pick the right one. So it has to satisfy this rule. Okay, so this is why this is important to go back and look at when you're working that problem. Hey, but this one works. Is everybody okay with that? See what I mean?
Is there ever going to be a time where multiple could work?
Oh, yeah. I mean, yeah, that's generally the truth. If you go back in and look at your, if I say you want to have a pH of, let's say, 6.5, you could probably, within the table of Kas or pKas, probably find 5 different buffers in there with conjugate acids that are going to work. Okay. So that's one reason I'm kind of narrowing it down to maybe 3 or 4, so you don't have to pour through the whole table. A lot of times it's like, what have I got on the shelf that'll work, you know, when you're actually in the business of doing this. Okay, so for item B, this is the other assumption which I've already told you. And that is we're going to assume the 3.0 molar refers to the total concentration of both components of the buffer. So now that we're a little bit more specific here, what we can say is that the 3.0 molar has to equal to the sum of the concentration of the NO2 1-, which is the conjugate base, and the original acid, which is the HNO2. So those 2 concentrations have to sum to 3.0. Okay? So I think we already stated that a little bit further above. All right, so now we're pretty much ready to set things up. We verified that we've got a good conjugate acid base pair here, and we've also made our assumption about concentration. So now we want to use the Henderson-Hasselbalch equation. And we know we can do this because we know we're setting up a buffer. So anytime we know we're dealing with a buffer, we can use Henderson-Hasselbalch. Now, does Henderson-Hasselbalch work if you don't have a buffer? What do you guys think?
No.
Could it technically, but it wouldn't really work out. Like you have the information, but it wouldn't be right.
It wouldn't work. It wouldn't work. You can't actually show that you've got a buffer there. I mean, you have to verify in advance that you've got a buffer solution before you can use Henderson-Hasselbalch. Otherwise, you're going to have to figure the problem out with some other direction, be it equilibrium or whatever, okay? through a normal ice table or something like that. But yes, that's exactly right. You can only use Henderson-Hasselbalch if you've got a buffer. And this is a mistake students make all the time. You know, I could ask you a question that just involves like finding the pH of like a weak acid, and somebody will throw Henderson-Hasselbalch at it. And I'm like, no, you can't do that. You don't have a base component there, so you don't have a buffer, okay? So that's the situation that we have. Now, granted, yes, you might make a tiny bit of a conjugate base when you let the acid dissociate. But remember, for a buffer to be effective, you have to have concentrations that are kind of close to each other. And when you've got one concentration that might be like 0.5 and the other one's 1 × 10⁻⁵, okay, that's no buffer. Okay, they have to be close to each other. All right, but in this case, it's perfectly fine. So I'm going to say that pH is equal to pKa plus the log, and now we can actually put real concentrations in here. Base over acid, right? So it's the concentration of the NO2 over the concentration of the HNO2. Okay, so we're working in terms of concentrations, so that's what we're going to use here. Now, the other thing that we know is that what we really have here is a situation where I have an equation where I can put a target pH in, I can stick a pKa in there, but then I've got that log term, and I don't know either of those concentrations, okay? So the problem is in that equation, I've got two unknowns, don't I? The concentration of the NO2 is an unknown, and the concentration of the HNO2 is an unknown. But what's the other thing that I have available to me? I have another equation, right? So anytime we have one equation and two unknowns, you guys know we need a system of equations, don't we? So I have that other equation up top there that I'm linking here, where I can say that the concentrations of the two buffer components have to sum to 3 molar. So what I can do here is I can, for example, solve for the nitrite ion concentration, and you could really do it from either direction, it doesn't matter. And that's equal to 3.00 minus the concentration of the HNO2. So that's kind of nice because now I've got this in terms of the same variable, because now I can make a simple substitution, right? I can take this thing, which is in terms of the acid, and plug it in up top for the base. Everybody see that? So now I end up with one equation and one unknown, don't I? So after I do that substitution, here's what I get. pH is equal to my pKa. Let's go ahead and actually plug numbers into it. Cut to the chase here. All right, so what did I say my target pH is? That was 3.00, right? It's equal to my pKa, which we went and looked up. That was 3.39. Okay, plus the log. Give ourselves lots of room here. It looks like what, 3.00 minus the concentration of the HNO2 over the concentration of the HNO2. Did I do that right? On my algebra good, guys?
Yep.
All right, excellent. So now notice, I've got this in terms of a single unknown, which is now just the concentration of the HNO2, okay? So now what I can do is just solve this thing. And if we want to just keep the math simple, we could just let that be like X and X there if I wanted to do that instead of writing that out every time. So now what do I do? All right, I'm just going to do a little algebra on this, right? So I'm going to bring the 3.39 to the other side, right? So that means I'm subtracting it from 3, which means I'm going to get a minus 0.39. Okay, what does that leave me with? Well, it leaves me with the log, and let's just rewrite it, of 3.00 minus X over X. And now what I'm trying to do is solve for X, right? Okay, but now here's the deal. The X is trapped in the argument of a log. So how do I get an X out of the argument of a log?
Raise it to the 10th power.
Yeah, I'm going to undo the log by exponentiating. So I'm going to do that to both sides. So I have a 10 to the minus 0.39. And then the log term goes away, right? So it's going to be 3.00 minus X over X. So right, raising 10 to the X on both sides undoes the log. All right, so that being the case, now it's just kind of getting some simple math done. So this number, when I actually work it out, just becomes a number, and that becomes 0.41. I think I'm okay on my sig figs there. Okay, so now I basically can just rewrite that as 0.41 is equal to 3.00 minus X over X. And now, can you solve that for X? Yeah. So basically, you got to get the X out of the denominator. So you end up getting 0.41 X is equal to 3.00 minus X. And now what do? We collect X's on one side, right? So the negative X becomes a positive X. So that becomes what? 1.41 X is equal to 3.00. Is that right? Now it's easy to solve for X, right? So now X turns out to be, when I go through this, what did I get? 2.13, is that right, guys?
Yeah.
What was X? That was equal to the concentration of the HNO2, wasn't it? Is that what we said X was? Yeah, that's what X was. So now, how do I get the concentration of the nitrite? Well, remember that second equation we had up there. Okay, we had the NO2 1 minus is 3.00 minus HNO2. So I have HNO2 now. So now it's get the nitrite, right? Okay, so what did we say it was? 3.00 minus that was my initial concentration, minus 2.13 molar. And that turns out to be what, 0.87? Everybody see what I did there?
Yep.
Okay, good. So now I've got both concentrations, right? I've got the concentration of the nitrous acid, and I've got the concentration of its conjugate base, the nitrite. Okay, so those are the concentrations I need. Now here's the situation. Now I have to go back and ask myself, all right, well, where are these things coming from? I know that these are the final concentrations I have to prepare in the buffer of each thing, but where are they coming from? So that's another thing in your homework you're going to see is that your reagents are actually going to be things that you have to add to the solution. So they might be, for example, a stock solution of a given concentration if it's an aqueous thing, or it might be, if it's a salt, a certain mass of the salt that you have to weigh out, right? Now, in terms of something like nitrous acid, okay, that's going to be a solution, right? Just like HCl or nitric acid is, and it's going to come in a certain concentration that you're going to use. But the other thing, how about the NO2, the nitrite? Where's that come from? Well, it's got to come from a salt of it, right? So in this case, we'll say it comes from, and this will all be given in your homework, so you know what your reagent options are. In this case, the NO2 comes from a solid NaNO2. That's a salt I can go to the stockroom and collect, right? So now I need the grams of the NaNO2 required to make the buffer. How much of the buffer did we say we were going to make? 0.5 liters, right? And we want this to be what, 0.87 molar? Okay, so that's the calculation we have to do. I need to have a mass of the stuff. So what do we do? Oh yeah, we got a volume and we got a molarity, so that means we can get to moles, can't we? Okay, so that's exactly where we're going to start. So we need a ½ liter of the buffer. I'm going to multiply it by the 0.87 moles of NO2 1 minus that I need per liter of the buffer, right? Okay, and now what am I going to do? I can get a mole-to-mole relationship between that and the salt, can't I? So for every 1 mole of NO2 minus, I need 1 mole of the salt, which is the NaNO2. Everybody see that? Per dissociation of the NaNO2, I get 1 NaO2 minus. Everybody see that? All right, so now, where do I go from there? Oh yeah, I need a molar mass, don't I? Because I got to get to grams of the salt that I actually went to the stockroom and collected. So for every 1 mole of NaNO2 that I get, I'm going to have, according to the periodic table, 69.0 grams of it. Okay, so that should give me the mass I need to go weigh out, right? Now, if we work this out, it turns out to be 30 grams of it. All right, so now I know when I go to make my buffer, I'm going to have to start by putting 30 grams of NaNO2 into my volumetric flask. Okay, that's going to take care of the base part of the buffer. Everybody okay with what I did there?
Wouldn't sig fig be 2 since half a liter is 0.50?
Probably. I'll just mark it as such. All right, so the next thing, how about the HNO2? Well, as I mentioned, that's an aqueous solution as it's prepared. So we're going to say that it comes as a stock solution at 10 molar concentration. All right, so what volume do I need? And again, what we're going to do is we're going to make 0.50 liters of buffer at a concentration of 2.13 molar in HNO2. Okay, so that's what I'm trying to figure out. So how would I do that part of the problem? What equation would I use to figure out what volume of the HNO2 stock I need?
A simple dilution.
Yeah, I can just do the dilution, can't I? So what does that look like? It looks like M concentrated, V concentrated equals M dilute, V dilute, right? And which one am I solving for here?
V concentrated.
Yeah, that seems right. So I got M dilute times V dilute divided by what? M concentrated, right? So what is M dilute? That's what, the 2.13 molar. That's what we ultimately want to end up with. What's the volume of the dilute? Oh yeah, that's the total volume of the buffer I want to make, which is 0.50 liters. Okay, and then what do we say M concentrated was? That's 10 molar, because that's the stock concentration. Okay, so molar cancels with molar, leaving me with liters, and that's exactly what I should have. And I get 0.11 liters. Sig fig's right this time, John.
Yep.
Okay, sorry, that shouldn't be molar, that should be liters. Or if we wanted to think of it, it would be 110 milliliters, right? So how would I ultimately make the buffer now? So I would go and get a vol flask, right? Probably what, a 500 ml vol flask, half a liter vol flask. I'd weigh out my NaNO2, 30 grams, put it in there. Maybe add a little water and dissolve it if I wanted to do that. Then I'd measure out 110 milliliters of my HNO2 stock, drop that in there as well. And then what would I do? I dilute the whole thing to the mark, wouldn't I? Then I cap it, invert it a bunch of times, and we're ready to use the buffer. Okay, so that's how we would do it. Okay, any questions about that? This is a good example because this is how people in the lab actually go and make buffers. And in fact, it's a lab that we used to do in quant, where we actually had you go make these calculations, and then you went into the lab and you actually made the buffer and tested it to see how close you got in terms of pH. But we're replacing it with the kombucha alcohol lab. So that's what you're doing next week instead. And this becomes a homework problem. Now we're not done yet. There's a part B. Part B involves changing the pH of the buffer. Now, why would we want to do this? Well, oftentimes when we actually make a buffer up, we find out the pH might be close to the target pH, but not exactly the same. Okay, and there could be various reasons for this. Okay, but say you're 1/10 of a pH unit high or low from where you want to be. Say you're at 3.10 instead of pH 3. Okay, how would I go about changing the pH of the buffer to get it to where I want it to be? Okay, well, tell me, what would I have to add to the buffer to change the pH from 3.1 down to 3? Just for sake of argument, what would I have to put in there?
Titrate a dilute strong acid or base.
Yeah, so in this case, you want to put a strong acid in there, right? Because you want to lower the pH from 3.1 down to 3, so you might add a strong acid. Okay, but what if you want to raise the pH by 1/10 of a pH unit? Well, you might throw a solution of a strong base in there. Okay, so yeah, generally we're going to change the pH of the buffer by adding a strong acid or strong base. And what that's going to do is it's going to adjust the acid and base parts of the buffer, just like we did in the prior example, example 2, to get them where we want them to be. So now we want to sort of estimate how much volume of a given strong acid or a strong base at a given concentration we need to add to make that happen. Okay. So let's, for the example of our buffer, let's say we want to ask ourselves, how do we change the pH of the buffer from 3.0, I think it's 3.00, to 2.80. Okay. So in this case, we want to run the pH down by 2/10 of a pH unit. So what are we going to have to add? Oh yeah, you guys know what we're going to have to add. We're going to have to add a strong acid. So now we ask ourselves, well, what strong acids are available to us? Okay. So in this case, we'll say that the strong acid available to us is going to be 12.1 molar HCl, right? Because that's how I get it out of the bottom. Okay, so that's the strong acid I have available. So the question now is, well, how much of it do I have to add to make this happen? All right. So let's set it up. So I'm going to set it up using Henderson-Hasselbalch again. So just to remind ourselves of what it says that pH is equal to pKa plus the log of the base part over the acid part, right? So the base part is what? The concentration of the NO2 minus over the acid part, which is the HNO2. All right, so we're going to work from the point of view of the Henderson-Hasselbalch. So now, what pH do I want to stick in there?
2.0 or 2.80.
2.80, yeah. We want to put our target pH in. This is where we want to end up. So this is why I'm using the 2.80. Does the pKa change?
No.
No, because that refers to the acid part of the buffer. That doesn't change. That's still 3.39. That's the pKa of the HNO2, the weak acid. So here's what we're going to do. We're going to show that change actually happening in the argument of the log. All right, so if I add an acid, and I can start by using my initial concentrations, right? So my initial concentration of the base from above was 0.87, wasn't it? And what was the initial concentration of the acid? That was 2.13. But now this is kind of like doing the ICF table within the argument of the log. So let's ask ourselves this. If I'm adding a strong acid, what's going to happen to the concentration of the NO2 minus? Is it going to go up or down? It's the base, right? So what's going to happen to its concentration if I add a strong acid?
Down.
It's going down. Now, I don't know how much it's going to go down. That's what I'm trying to find out. So I'm going to just put an X there. Now, if you remember back from the ICF table that we did, if I lose X of the base, what happens to the acid? What do I have to do to the 2.13?
Don't you lose it as well?
I don't lose it. Go back and look at your ICF table.
You'd add it.
I add it, right? Because what am I doing? I'm converting some of the base, the NO2 minus, to its conjugate acid. I'm protonating it, right? So that means I have to add X. So all I'm doing here is converting base to acid in my ratio here. And I'm doing that by adding, and I can show it here. It's this reaction. It's NO2 minus plus the hydronium ion coming from the strong acid, right? And then what are you going to make? You're going to make HNO2 and H2O, right? So if I'm losing X of that, I have to be making X of that. Does it make sense?
Yeah.
Okay, good. All right, so that's how I got to that equation. So now, how do I solve the equation? Now it's just simply doing algebra, isn't it? So I can bring the 3.39 over to the other side. When you do that, you end up getting minus 0.59, and you guys can check the, I'll check my algebra as I go. And that's equal to the log of 0.87 minus X and 2.13 plus X. Now I got to isolate X's, right? So I exponentiate. So I'm going to raise both of these 10 to the power, right? So 10 to the minus 0.59 becomes a number. That becomes 0.26. And then what happens when I raise a log, 10 to the log power? It undoes the log, right? So now I've got 0.87 minus X. And I've got 2.13 plus X. So now you do some algebra on this, right? Now, I'm going to leave it to you guys to go through the algebra and get X. And I went ahead and solved for X, and this is what I've got. And you guys make sure you can do this. It's just multiplying both sides by something and distributing and then collecting like terms. You end up with a 0.25 molar. And what is that equal to? Well, it's equal to the concentration of the hydronium ion I've got to get in there to affect that change, right? Because I can go back to my equation up here and recognize that if I have minus X of the hydronium ion, I'm going to lose that same X of the nitrite and convert it to the same X of HNO2. So now I have the concentration of the hydronium ion. So now, how do I determine how much of the stock I need? Well, again, we're dealing with two solutions, so it's just a dilution equation again, right? So it's the molarity of the concentrated times the volume of the concentrated, which is the molarity of the dilute times the volume of the dilute. And I want the volume of the concentrated again, don't I? It's how much of the strong acid I have to add to make this happen. It's the molarity of the dilute times the volume of the dilute divided by the molarity of the concentrated. Okay, so the molarity of the dilute, that's the 0.25 molar we just figured out. The volume of the dilute, okay, that's the total volume of my buffer. Now keep in mind, I'm not accounting for the fact that I'm actually adding a little bit of liquid to this. I'm keeping the volume of the buffer the same. even though I recognize I'm actually adding a little more liquid to it. I'm neglecting that. And the molarity of the concentrated is the 12.1 molar. Okay, so molar cancels with molar. So the volume of the concentrated I have to add to the buffer to affect the change turns out to be about 0.010 liters. Okay, it looks like sig figs are okay. And that turns out to be what, 10 mils of my HCl concentrated. Okay, so that's the volume of the concentrated acid I'd have to add to my buffer to adjust the pH downwards by 0.2 pH units. Okay, so that's basically what your homework is going to look like once I put it together and give it to you. The only difference is everybody's going to have a different target pH, and you're going to have your choice of conjugate acid base pairs. And we're also going to put a change in there. So some of you guys will be changing your buffer upwards in pH, and some of you guys chemical reagents and stock solutions you have at your availability to make that happen. All right, any questions, guys? Okay, so again, for lab next week, since this is the last time I'll see you, expect a quiz, probably on buffer related stuff, because that's kind of what we've been doing. Also, your lab, for those of you who've completed it, your lab will be due. Okay, so that means have your pH plots and all of your data put together for me. So there's actually a fair bit of data work up in this lab, so don't wait to the last minute to get on top of it. And if questions arise with any of those plots, pH plot, first derivative plot, all that stuff, you know, just come to my office hours and we'll look at it together. Be prepared to share a screen and so I can see what you're doing. Other than that, no homework due next week, but you'll get a new assignment with the buffer.
Quick
all right,
question.
anything else, guys?
Yeah,
go
quick
ahead.
question. You said that this was the last time we'll meet before lab. Are we not going to have class on Monday?
I guess we will, yeah.
Oh, okay.
Actually,
I was worried.
There's actually an outside chance that we may not. I think I will. I'm getting my COVID vaccination on Monday, and it's scheduled for like 11:30 in the morning. I should definitely, unless there's like an hour wait, I should definitely be back by 3:30 to teach the class. Yeah, but we'll remind you of all this stuff again. I always think Wednesday to Tuesday. Yeah, I forget I actually get to teach you guys on Monday. So the next thing I'll do is I'm making a few minor tweaks to the kombucha alcohol lab that we're going to do next week. So that's on my desktop right now. Once I have that done, I'm going to go ahead and post that out to you guys on D2L so you'll have it. So be prepared and looking for that. All right, and I think that's the only other thing we need to worry about. So new lab next time. And then on Monday, we'll actually talk about that lab a little bit because I'm pretty much done with buffers at this point in pHs. So we'll talk about some background on the kombucha lab at that point. Anything else? Okay, guys, I'll see you on Monday then.
All right, have a good one.
All right, you guys too.